Welcome everybody to another seminar, Logicians in Quarantine. On behalf of the Brazilian Logic Society and of the Logic Interest Group of the Brazilian Computer Society, it's a pleasure to have you all here. So I would like to thank you very much, Professor Mario Benevides, who accepted to give us a talk, and we'll talk about what makes a logic dynamic. Mario, thank you very much.
Thank you. Good afternoon, everybody. First of all, I would like to thank the organizers for this nice series of seminars, Bruno, Petrúcio, the Brazilian Logic Society. And my name is Mario Benevides. I am from Instituto de Computação, Universidade Federal Fluminense, in Niterói, Rio de Janeiro. And we are going to talk about dynamic logics. So just an outline of the talk. We'll talk about propositional dynamic logic, some extension, multi-agent epistemic logic, dynamic epistemic logic, and then some dynamic logic that manipulates data structure like memory logic or PDL with structure states. And if you have time, you'll talk about some other extensions of propositional dynamic logic. So if you go to a dictionary and look up for the word dynamic, you're going to find something like constant change, activity, progress, action, event, progress, update, assignment. In some sense, dynamic logic is about all this words like changing, activity, update, assignment, and so on. So just an overview, dynamic logic, there are lots of streams nowadays, but the three broad categories are dynamic logic for program specification, where modalities are programs. Dynamic logic is action logic in AI for planning, reason about actions. Modalities are actions performed by agents. And dynamic epistemic logic, that are logic for reason about knowledge. Modalities are epistemic action performed by agents. These are actions that change agents' knowledge and beliefs. So dynamic logic started in the middle 70s, but it was strongly influenced by this idea of automatic program verification, but the modal approach is from the middle 70s. There are two nice papers that influence all this area of verification of imperative programs, one by Floyd, another one by Hoare, and they conceived what we call Floyd and Hoare logic in the end of the 60s. Floyd and Hoare logic is based on a triple. We have a formula, program, and a formula. And the idea, if the precondition phi holds, then after the execution of the program, the postcondition must hold. The idea is to prove correctness of the program. So if the program satisfies some preconditions, it must end up in a state where the post-conditions are satisfied. So Floyd and Hoare logic is a kind of sequence calculus. You have these axioms, you have inference rules for sequential composition, if then else, why. I just put the rules here for have a taste of how the rules look like. And then you can prove the correctness of a program. For instance, this program here, if you start with x equal to 1, then the program will finish with z equal to 2. So you start the axioms, then you manipulate the axioms and get the program, the Hoare triple, that was the precondition, program, and postcondition. You can have more sophisticated programs, but the idea is to have this kind of proof system to prove that a program is starting in a state satisfying the precondition, and up in a state where the postcondition is satisfied. So in the middle 70s, Pratt came about with this idea of translating Floyd and Hoare calculus to a model calculus. So he took the Floyd and Hoare tuple and translated this for modal logic, for something that he called dynamic logic. The translation is straightforward. You translate the precondition for if phi implies that for all execution of pi, the psi holds. So this idea is a model version of Hoare logic. You can have a translation, a direct translation for dynamic logic, and you have one modality for each program. This was an interesting idea. So why to use modal logic and not staying with Freudenhofer logic, using first-order logic for express your properties? And there are two interesting problems when we talk about logic and computation. That one is satisfaction. Given a formula phi and a structure E, we want to know if phi holds at E. And the validity problem that given a formula phi, we want to know if there exists a structure E where phi holds. And you can define these two problems over finite structures as well. So the problem is first order logic, satisfaction is undecidable, validity is undecidable. Even over finite structure, modal checking is space complete, that's in general is quite bad. And validity is also undecidable. If you go to modal logic, satisfaction is decidable in general. We have modal logic that are undecidable, but we are not interested in this modal logic here. Satisfaction is undecidable, validity is undecidable, satisfaction is decidable, validity is decidable. Over finite structure, in general, modal checking is linear in the size of the formula times the size of the model, and validity is decidable. Just an overview, the complexity of modal logic in general, modal checking is linear. Validity goes from NP complete P space, some X time, but in general, they are decidable. In general, modal checking is linear. So some historical remarks. We start with Pratt in the middle 70s. Then 1 year later, Fischer and Ladner proved finite model property and decidability, a beautiful paper. And then Segeberg gave the first completeness proof with some gaps, but he proposed some induction axiom to express the iteration operation that are quite nice and quite popular nowadays. And Parikh, 2 years later, fixed the completeness proof and then gave a shorter proof. So Segeberg took this idea of the iteration. The idea came from something called ancestral logic that he proposed in the 70s as well. And ancestral logic is a logic to talk about ancestral. You have some modal logic with some modality, a box that runs over accessibility relation R. And you have a box star that runs over accessibility, the reflexive transitive closure of the accessibility relation. And you have these two axioms that are quite nice. The last one it has some similarity with the induction axiom of piano arithmetic. If you see here, this axiom says that if you have phi and you have phi, you prove that in everywhere phi implies that all states accessible from now, you have phi as well, so you have phi in all your models. So this is a kind of induction. It's a quite clever axiom, and it's quite nice. So in general, dynamic logic talk about action, basic programs, in induction. Most of the dynamic logic has some kind of fixed point operator, like reflexive transitive closure, iteration, least or greatest fixed point, like in the mu calculus, finite paths, like in CTL star. So another day I was watching a talk in the supergroup, and a guy proposed a modal logic without an induction axiom. And the first question that someone asked in the audience was, but you call a logic dynamic, but you don't have some kind of fixed point. So this is some feature that in most of dynamic logic, you find some kind of fixed point. So the motivation for dynamic logic was a logic to reason about programs, correctness of programs, equivalence of programs, specific power of program constructs, synthesis of programs from specifications. And you can see it as a mixture of first-order logic, modal logic, and algebra of programs. But here you have something interesting, because in first-order logic, when you have free variables, you have evaluation. Evaluation is static. Once you gave evaluation for a free variable, you evaluate the formula for this evaluation. But in dynamic logic, you have assignment. Assignment is it changes the values of variables. For instance, if you assign to x plus 1 over the naturals, we change the truth value of x even to true, to false, to true. So we have this kind of dynamic when you have assignment. But we want to talk about propositional dynamic logic, and this talk is a propositional version of dynamic logic. It's a logic to reason about programs that are independent of the domain. We don't have an assignment to variables. And we are going to talk about a specific propositional dynamic logic called dynamic logic for regular programs, where you have a modal logic and programs are regular expressions. And it's a multimodal logic with two modalities, one box and one diamond. And for each program, you have two modalities, one box, one diamond. We start with basic programs, and then you have sequential composition, non-deterministic choice, iteration, and test. Sequential composition will execute alpha and then beta. Non-deterministic choice will execute alpha or beta. Test will test if phi is true in the current state. If it's true, we proceed. If it's false, we fail. And we have iteration that will execute alpha a finite number of times. So formulas are, in general, the same formulas as modal logic. We have diamonds and boxes, but we have programs now. We have basic programs, have sequential composition, non-deterministic choice, iteration, and test. So one question is why we choose regular expression instead of choosing other sets of programs operator. We could have chosen, because you can define if then else using regular expression, you can define transitive closure, while, repeat, abort, and so on. So this is just a choice. So the semantic is rather standard for modal logic. You have this notion of model, which is based on a frame that's a set of points, a relation A for each basic program, and you can inductively define the relation for non-basic program as the sequential composition is the composition of relation, non-deterministic choice is the union of relation, test is a subset of the identity, and the iteration is the reflexive transitive closure. So then you have the notion of satisfaction standard for modal logic. You have the Booleans, you have the diamond, that is true if there is an accessible state where phi is true. We have the box that in all accessible states phi is true. And you have a beautiful axiomatization, and with 5 axioms, 5 and 6 are the Segeberg induction axioms that are quite nice. And you can prove that PDL is sound, complete, with respect to the class of finite PDL models. It is decidable, the complexity of the validity probably has time complete, the complexity of model check speed time, and it's not compact. What we would expect once you have this fixed point operator. So we can have other variants of PDL, like we could restrict our programs to deterministic programs, basic programs. We could have converse that you can undo a program. We could restrict tests for only test Booleans, for instance. We could have context-free programs, for instance, a recursion. We could have intersection, complement. We could add constant, nominal, binders, and have a hybrid propositional dynamic logic. And one nice thing that most classical extensions preserve good properties of PDL, like decidability, SP-time completeness, modal checking P-time. We must be careful with these last 3 here, but I'm not going to comment this now. So let's talk about now multi-agent epistemic logic. Multi-agent epistemic logic are a modal logic used to represent and reason about group of agents or agents' knowledge and belief. We have a language with a finite set of agents. We have the Booleans. We have three boxes. One box that KA phi, agent A knows phi, EG phi, everyone in the group G knows phi, and CG phi, it is common knowledge among the members of the group G that phi holds. We could have the dual BA phi. Normally, some people call it the belief. I prefer to call it dual. The semantic is rather standard as well. It's based on a frame, it's a set of states. We have a binary relation for each agent, in general expressing the doubts of the agents. And you have the relation RG, that is a relation for a group, that is the union of relation of each individual in the group. And you have the reflexive transitive closure of the relation of the group. So the notion of satisfaction is rather standard as well. Each modal, each of the box K, A, E, G, C, G runs over its own relation, relation A, relation G, and relation G star. We have a beautiful set of axioms with five. First, the epistemic logic axiom, and here you can see Segeberg axioms again, 7 and 8. Because the common knowledge is the transitive closure of the union of the relation of the group. And we can see multi-agent epistemic logic as a dynamic logic. If you translate your agents as actions, you translate your modality KA phi as box A phi, BA phi as diamond A phi, EG phi as the non-deterministic choice of the agents in the group, and the common knowledge as the non-deterministic choice of the interaction of the elements of the group. So in this sense, multi-agent epistemic logic is a fragment of dynamic logic. And it is quite interesting because if you look, we don't have sequential composition. We could add more PDL operators and have other kinds of knowledge, common knowledge that we are in general do not express in multi-agent epistemic logic. So this is something that is not very well explored. So let's have a look at an example. We have a 3-card game. We have 3 cards, 0, 1, and 2. 3 children, Annie, Beth, and Clara. Each child receives 1 card. They know their own card, but they don't know the card of the other children. We have propositions 0A, 1A, 2A to express that Anna has 0, 1, or 2, or Bob, or Clara. And we give name to states as using a positional notation. State 0, 1, 2 is the state where Anna has 0, Bob has 1, and Clara has 2. So as you have 3 cards, you have 6 combinations of the cards. So you have a 6 possible states, 0, 1, 2, 0, 2, 1, and so on. And the edges express the doubts of agents. 0, 1, 2, under the point of view of N, she cannot distinguish 0, 1, 2 for 0, 2, 1 because she has card 0, but she doesn't know if Bob has card 1 or 2, or Clara has card 1 or 2, and the same is for 1, 0, 2, 1, 2, 0, and 2, 0, 1, and 2, 1, 0. So these are the doubts of Bob, and these are the doubts of Clara. And we can evaluate formulas like Bob believes that Anna has card 0, or Bob believes that Clara knows that Clara has card 2, and so on. So what are dynamic epistemic logic? Dynamic epistemic logic are multi-epistemic logic plus epistemic actions. Epistemic actions are actions that change the epistemic state of agents, change agents' knowledge and beliefs. We can have public action, like someone, action that all agents know the content of the action, like broadcasting a message, or someone takes a microphone and makes the announcement. Or you could have private actions, actions that only the agents involved know the content of the action. One agent sends a message to another agent, for instance. So the most popular dynamic epistemic logic nowadays are public announcement and action models logic, public announcement for public actions, and action models for private actions. So let's go back to the three cards game again. We have this model, and then Annie announced publicly that she doesn't have card 1. So once Annie announced that she doesn't have card 1, now Bob and Clara knows that state 102 and state 120 are not possible anymore. So they don't make sense anymore. So the model needs to be updated. So we must update the model now, erasing the states 102 and 120. And the idea of public announcement logic is to extend the logic of multi-agent epistemic logic with a new modality that is, meaning after the announcement of phi, it is the case that phi decide. So, for instance, after the announcement, not 1A, Anna does not have card 1, Clara knows that Anna has card 0. So the effect of public announcement is a restriction in the model in order to have only state where phi is true. If I announce publicly phi, I restrict the model to have only states where phi is true. So the idea is announcements are always true. So in order to evaluate the formula, announce phi and then psi is true in a state S, phi must be true in S, and then we will restrict the model and evaluate psi in this same state. This is just a restriction. We restrict to states where phi holds. So we have a nice axiomatization. Again, you can have common knowledge, and so on. So what are action models? Action models are another dynamic logic to model epistemic actions, but now we want to express private communication action between agents. Agents that everybody knows that the action has happened, but only the agents involved know the content of the action. For instance, a player shows his card to another player, a player whispers some information in the ear of the other player. So let's go back to the three-card game again. Now Anne shows her card to Bobby. Clara does not see which card was shown, but Clara saw that some card has been shown. So after Anne showed the card to Bobby, Bobby doesn't have doubt anymore. Now he knows everything. So the new model is this one. We have to erase the edge, the edge that represents the doubts of Bob. Just a minute, please. So, how can we do that? Action models is something quite clever. Now we have the epistemic model that is the model of the doubts, but we also have an action model that is doubt about which action was performed. Let's go back to the example. For instance, Annie could have shown card 0, 1, or 2. So there are three possible actions that Annie could have performed: show card 0, 1, or 2. Under the point of view of Bob and Annie, they don't have any doubt which of the action was performed. But Clara doesn't know if it was shown card 0, 1, or 2. So this is the action model. It's a model that expresses the doubts about the actions that are going to be performed. And we must have a precondition. In order to show 0, we must have 0. Show 1, she must have 1. Show 2, she must have 2. So we have this definition of product. I'm not going into that, but once you do the product of these two models, we have this model on the right-hand side. And that is the model, the updated model now after the communication between Anne and Bob. Anne has shown the card to Bob. So dynamic epistemic logic are like public announcement action model. They evaluate the resulting formula in a different model, in a restricted model. And this is why they are called dynamic. Here, dynamic express another thing. It express that the model is changing. You are evaluating your formulas in a restricted model or in some kind of different model. And then one question that comes about is, and if you add iteration to this dynamic logic, that would be nice. That in general doesn't work very well. We can get undecidability very easy. There is a nice paper by Miller and Morse about the undecidability of iterated model relativization to the logic, and it's very interesting. Another logic that changed the structure of model is swop logic. And a swop operator, the dynamic model, the swop operator changed the model during the evaluation. The idea is you have operator diamond S that swaps the direction of arrows when traveling through the arrows. It inverts the arrow. For instance, if you have this model here and you want to evaluate a formula in state W, then you have this formula diamond Q. Diamond Q will be false because we go to the state where P is true, and there is no state that you cannot see that Q is true. But if you change it for this swap modality, then you can go to the state, this state here, and change the arrow. And now the diamond Q is true. So the idea is to change the model and evaluate the formula in a different model. So all this logic have in common, like public announcement and action model and swap logic, is they are logic that you have some operators that change you evaluate your formulas in different models, in a restriction or in a different model. So now we want to talk about another kind of dynamic logic, that are dynamic logic that has some kind of means of data manipulation. The idea is to reason about data manipulation. If you think of PDL or modal logic in general, states have no internal structure. States are just a set of points. And we're going to talk about some memory logic or some logic that are inspired in separation logic, like dynamic separation logic and so on. So memory logic are logic with operator that can memorize and retrieve the current state from a memory. Models are equipped with some memory. We extend the notion of models that we had in modal logic now with a new model with a memory M that is a subset of the set of states. And we have two model operator. One is remember. Remember, when you perform remember in the state W, you add W to the memory and then evaluate file. And known is just a test. Known, if you evaluate known in a state W, you test if W is in the memory. If it is, you continue. It's not, it fails. So we want to talk, this is a kind of data structure. You have a memory associated with your model, and you have this operation of remember a state, putting a state in the memory and retrieving it from the memory. But now I would like to talk about an approach that was from our group, that states are pairs, and you want to have an operation of store, recover the current state in the first and the second coordinates of the pair. For instance, operation of store one, if you store one in the state S, you perform store one in the state S, you go to a state that is a pair and S is the first coordinate. If you give return, recover, In a state ST, recover 1, you go to state S. So just an outline, a general outline. The idea is to add structure to states. Is an extension of PDL inspired in fork algebras. We're going to have PDL with storing, recovering, and parallel composition. And this is a series of joint work with Paulo Veloso, Sheila, Petrúcio, and Renata. I think everybody is here in the talk. And what are fork algebra? Fork algebra are relational algebra with an extra operator of fork. And the domain must be closed under a pairing operation. That is quite clever idea. Yielding a structural universe, then a rather set of pairs of points. So the language is the language of PDL plus 4 basic programs for atomic problems: store 1 and store 2, storing the first and second coordinate, recover 1, recover 2 from the first and second coordinate, and parallel composition. States are ordered pairs. And for instance, store 1 is you perform store 1 in a state S, you go to a state that is a pair where S is the first component. If you perform store 2 in a state in the state S, you go to a state that is a pair and S is the second component. And recovery is the converse. If you are in the state ST and you run recover 1, you go to state S. If you go to perform recover 2 in the state ST, you go to T. These are the projections. And parallel composition, in order to perform parallel composition, you must start in a state that's a pair, S1, T1. Then you perform P1 in state S1 yielding state S2, P2 in state T1 yielding state T2, and the resulting state is S2, T2. This is a real parallel operator. So the language is the PDL extended with parallel composition, store 1, store 2, recover 1, recover 2. And formulas are interpreted on sets of structured states. A structured state is a pair. Now you don't have only set of states. You have a structured set of states that's a pair. S is a finite, it's a non-empty set. And the star is a pairing operation. That's the only requirement is that it is injective. So a structure frame is a frame that is based on the structure set, and you have the structure set, and you have one relation for each program. And the structure model is a model based on the structure frame. So the satisfaction is rather standard. If you want to evaluate Dynamo S1 phi in the state S, you must, there exists an accessible state from S where phi holds, the state is T, and T is equal to S R. There is a next state where phi holds and S is the first component of this state. The same interpretation for S2, and then it's similar for recovery. If you want to evaluate recovery 1, Dynamo recovery 1 phi in the state S, so S must be a pair, like TU, and in T, that is the first component, phi that must hold. And the parallel composition, it's also similar. If you want to evaluate Dynamo pi 1 parallel with Dynamo pi 2 phi in the state S, S must be a pair, S1, S2. Then you run pi 1 in S1 yielding T1, you run pi 2 in S2 yielding T2, and in this new pair T1, T2, phi must hold. So just having a look in a simple example, you want to have an example that this is a program, this program pi1. We start pi1, we store the current state. For instance, let's have a look in the diagram. We start in the state U, then we store U in the second component, and then perform alpha in the first component. One is the identity. So it does nothing. We perform alpha in the first component, goes to V1. Beta in the first component again gets V1 and U, and then restore U and go back to state U. So we have this memory. We can go back to state and start continue evaluating formulas there. So this is a nice piece of work. It's something that I am interested at the moment, and the idea is to add the structure to states. It's an extension of PDL inspired in fork algebra. We have PDL with storing, recovering, parallel composition. The idea is generalize cryptic semantic with structure sets of possible states. The idea is to reason about data manipulation. So the last remarks, almost finishing. We could have PDL with a stronger extension. For instance, we said in the beginning of the talk that PDL was a kind of propositional modal logic plus algebra of regular expressions. Why of studying algebra of regular expression, we could have some process algebra, some more expressive algebra, for instance. And this is what I have been working for some time, is to, for instance, to have PDL with CCS program. CCS is a process algebra proposed by Robin Milner, as calculus for communicating system. And the PyCalculus is an extension of CCS for mobile program process. And I have been working with this process. It's quite interesting. We have been working also with Petri nets with Bruno and Herman. We encode Petri nets as a PDL programs and then reason about PDL specifications and so on. So there are some, this work is still in the beginning. We will have lots of things to do here. So just finishing, we've shown some dynamic logics here, propositional dynamic logic, the idea that in general dynamic logic, propositional dynamic logic has some kind of fixed point operation. We have multi-agent epistemic logic that can be seen as a dynamic logic. We talk about dynamic epistemic logic that in some sense are a bit different. The dynamic component here is about evaluation in a restricted model. When you perform these actions, you evaluate your resulting formula in a restriction of the model or some operation in the model. We have talked about PDL with data structure, for instance, like memory logic, and PDL with structure states. And that's this logic as well. In some sense, you change the model and you add things to memory and you retrieve. So there are dynamic logic. And so this is quite a tendency nowadays. You have this, say, propositional dynamic separation logic, that are logic also that you have data and your model keeping changing. And you have this other extension of PDL, like PDL for Petri nets and with process algebras and so on. So the last slide, I would like to make some kind of advertisement. We have this DALI workshop on dynamic logic, new trends and application. The deadline is now, is July 25th. It was going to happen in Prague, but now I think it's going to be online in October. And we are going to have procedures, the post procedure by Springer, lecture notes in computer science. And we are planning a special issue from the Journal of Logic and Algebraic Math. The last two editions we have published these two the spring in the JLAMP special issue. So everybody's very welcome to submit a paper. Thank you very much. So this is the end.
Thank you very much, Mario.
40 minutes.
So now I have some time for questions and comments, interactions with the speaker. So I just would like to ask you to manifestate in the chat if you'd like to make some question or remark, comment, anything. Just to avoid a lot of people talking at the same time.
Alô, Bruno?
O Carlos deve estar digitando.
Ah, tá.
No, so I already did it, so I was waiting for you to tell me.
Oh,
so
okay.
Can I?
Yes, sure.
Yes. Hi, Carlos. How are you?
Hey, hi,
Nice
Mario.
to talk to you.
How are you? So, thanks for the talk. So it was very nice to see. I'm going to put the camera. So it was very nice to see all this PDL summarized with different applications. So it was very nice to see your talk. So my question is related to process calculi, to CCS in particular, or also the pi calculus. So as far as I understood from your rules, you have sort of so the semantics of the parallel operator is through concurrency. So the both terms has to evolve. It's not interleaving, right? So T1 has.
The PDL CCS is interleaving.
But when I saw the rules, was like the two components has to move.
No, this is in the PDL with parallel composition. Yes, with the one with structure state is true parallel, but it's not oh, sorry.
Sorry, so for the CCS, you have a different one. So
I have a different one. Yeah, it's interleaving. It's like in the CCS, you have this kind of shaking hand and handshaking.
Okay, and do you have a result like the one of Hennessy-Milner that by similar processes, they satisfy the same formulas in your logic?
Yes, yes.
Nice, and also this work for the pi calculus?
We never, because we published a paper with the CCS, and then when we finished the pi calculus, we published a conference paper, and the student that was Luis Menacha, he finished his PhD. So we never went back, we never go back to this pi calculus extension. So for the CCS we proved, but for the pi calculus we didn't prove the Hennessy-Milner theorem.
Okay. Okay, thanks a lot, Mario. That's it.
Valéria?
Oi, Mário, tudo bom?
Valéria, tudo bom.
Uma palestra super legal, adorei. Adorei. Eu quero fazer pedidos agora. Eu tenho uma perguntinha pequena, mas eu queria fazer um pedido assim de ver se você podia fazer essa survey que você fez da complexidade inicial, se dava para tentar pensar numa survey que fosse sobre a complexidade no caso intuicionista, né? Já que vocês têm um grupo tão grandinho aí de gente pensando nisso, seria bem legal ter uma survey de complexidade pensando nessas coisas mais construtivas. Esse é o pedido para o futuro, assim, daqui a algum tempão. E a pergunta mais ou menos fácil é que eu queria saber qual é a intuição que as fork álgebras trazem e se por acaso, assim, por que é que você acha que a gente tem que fazer, você tem que fazer recovery nas duas coordenadas e tem que fazer storage nas duas coordenadas? Por que as coordenadas nesse caso?
Porque vem de fork álgebra, a ideia de fork álgebra é o estado vai representar a sua estrutura de dados. Você pode pensar depende de como que você manipula as coordenadas, você pode ter uma pilha, uma fila, porque agora você vai ter pares de pares, de pares, de pares, você vai aninhando.
Uhum.
Então, a ideia é que você vai precisar colocar dados e pegar dados, e com essas projeções e colocando coisas, criando pares e projetando, você consegue manipular, fazer essas operações de pilha. Tem uns artigos do Veloso com o Armando e o Frias, que eles fazem várias dessas estruturas de dados e várias coisas em fork álgebra. Então, a ideia foi basicamente essa.
Entendi. Então, é realmente simplesmente fazer pairing, fazer empareamento, fazer pair a par para a estrutura de dados, né?
Isso.
De distribuir e de injetar.
Exatamente.
Entendi. Obrigada. Não, valeu. Mas agora pensa com carinho na minha sugestão, tá?
A gente podia voltar a pensar nessas coisas de lógica modal intuicionística. Eu acabei... Essa semana eu estou até interessado, porque eu voltei outro dia, eu tive que usar aqueles axiomas de Steve Fish, né, para...
Legal. Sim. Pensa com carinho. Obrigada, valeu.
So, Nikolai, would you like to talk or just type?
Está no chat, Bruno?
Sim. It looks like he's not in the room anymore. Maybe he had some problem. Well,
hello, Nikolai?
He's not in the room anymore.
But I can give some word, don't mind. Maybe he can listen.
It will be recorded.
PDL without star is very well behaved. It's like a modal logic. There is no problem. But the problem here is star is a problem. If you have one action and star, you get S-time completeness. So star is something that always change the completeness. Everything that has star goes to S-time or sometimes to S-time. For instance, those logic of CCS, PDL, CCS, they are true S-time. And because the interaction between the star and the parallel composition is quite problematic. But the star always jump the complexity of your logic from pre-space to S-time. And there is a nice paper, I think, from Segeberg, that you only need one basic action and star, and you have S-time completeness. So star is always a hard thing to compute.
So do we have any other question or comment? Well, so thank you very much again, Mario. As you know, I'm a dynamic logic enthusiastic. It was a really nice presentation.
Thank you.
And thank you, everybody who is here. And in the next week, we will have Alejandro Diaz-Caro, who will talk about extensional proofs in propositional logic.
Okay.
I'm just going to finish the recording.
Bruno,